Hello and welcome to the Isabellenhütte online video tutorial IVT 3.0 B-sample configuration with Bussmaster. This video tutorial has 5 chapters: configuring and ordering your IVT 3.0, parts and wiring, the IVT 3.0 CAN structure and the BMS control message, IVT 3.0 high voltage channel configuration, and interpreting the IVT 3.0 CAN result messages. In this chapter, we're going to talk about the IVT 3.0 CAN structure as well as the use of the BMS control message. Please note that Bussmaster has to be configured just like it was described in the corresponding chapter of the IVTS tutorial video in Chapter 2, Setting up Bussmaster. For this chapter, we will need to have Bussmaster installed on your machine. We're using version 3.2.2, but any other recent version or successor version should do the job as well. And you have to have installed the peak CAN to USB drivers in case you're using the peak CAN to USB transceiver to connect your IVT 3.0 B-sample to your computer. Also, we will need the IVT 3.0 CAN DBC file that can be obtained from your local Isabellenhütte representative or one of our partners. Now, I went ahead and opened the Bussmaster program, as you can see on my screen, and I uploaded and converted the CAN DBC file for the IVT 3.0 B-sample. And you can see in the database editor here what the CAN structure of the IVT 3.0 B-sample looks like. Generally, the IVT 3.0 CAN protocol is quite a little different from the former IVTS CAN protocol. We have mostly result messages and the UDS diagnostic messages down here, as well as one message that actually enables us to do some configuration, which is the BMS IVT control message that we're going to have a closer look at later on. Generally, those result messages are defined in a certain way. Every result message contains one message counter and one CRC checksum per message. This is just one requirement that comes from the ISO 26262 functional safety standard, and also our result messages are structured in a way that there's usually 2 results per message that are communicated. In this case, it is the first voltage channel, which we call high voltage battery, because it's supposed to be connected to the other pole of the battery depending on where IVT 3.0 is installed, and the actual primary current sensing signal. And every result within the message has one status indicator here, the current status in that case, and the high voltage battery status. All the other result messages are structured in a similar way. You always have one CRC, checksum and message counter per message, a status per result message, and then usually 2 results per result message. But we'll look at these result messages in more detail in the last chapter of this video tutorial. Also, the placement of the voltage sensing points will be explained further in the next chapter of this video tutorial. That also dives into the isolation measurement functionality and the isolation measurement result messages here. At this point, I just wanted to explain the structure of these messages and what different components you see within each of these messages. Right now, we want to look at the BMS IVT control message and what you can configure here and what you have to do in order to get the B sample to work for you. The IVT control message enables the customer to give input about the states of relays and fuses to the IVT module and also control some functionality of the IVT module. Like all the other messages too, the IVT BMS control message has a message counter. This is a 4-bit counter. This function is still disabled in the B sample stage. And also, like all the other messages, it has one checksum message, but also this is still disabled and therefore can be disregarded. The CRC checksum will be also defined in the CAN protocol, and it can be customized, and it works according to the auto SAR profile. Apart from that, the IVT 3.0 module can be fed with the state of 3 relays: the pre-charge relay, the main relay on the plus and on the minus side. And basically there's 2 states that these bits can have. It's either closed and the signal value would be 1, or open, and for this the signal value would be 0. This information would have to come from the main BMS controller on the customer side. The same is true for the fuse state. Also here there's 2 states that this bit can have. It's fuse plus and fuse minus are closed and the signal value would be 1, and one of the fuses, either plus or minus, is open. In this case, the signal value is 0. Lastly, the customer has the possibility here to enable or disable the isolation measurement functionality of the module, and the bit states here are either 1 for enabled or 0 for disabled. In the next step, we will connect IVT 3.0 to Bussmaster, and we will have a look at how to configure the IVT BMS control message. So I went ahead and I closed the DBC viewer window, and I have my transmission window open in my message window here in Bussmaster, and I pulled up BMS IVT control message here. And now important for the IVT 3.0 B sample to work is that all the relays are closed, so they have to have the value of 1, which means that they're closed, and also the fuse state has to be set to 1, which I'm doing right now. So the module gets the information from the battery management system that the whole circuit is operational. To enable the isolation measurement here is not necessary for the module to work, and as we don't have isolation monitoring enabled in this test system, we're going to leave this value at 0. Now the B sample is programmed in a way that it will go to sleep mode after 5 seconds if it doesn't receive a BMS control message, and this is the important part. So In order for the module to keep sending result messages, you have to configure the control message in a cyclic way. So you have to choose a certain repetition time up here for this message to be sent out. We can leave that at the default value of 10 milliseconds. It has to be set to at least a value below 5 seconds because, as I said, after 5 seconds the module will go into sleep mode. So in order not to overload the bus too much, I'm gonna set this to 1 second to 1000 milliseconds, and I'll enable the little checkbox here under repetition, so this message is sent out every 1000 milliseconds. The module is up and running. As you can see, we get all these result messages in, and in the next chapter we will have a more detailed look into how to actually place the sensing points of all these high voltage measurements, and after that we will dive a little bit more into these result messages and their interpretation.